Section: Introduction. In this section, we introduce Think and Execute, a framework that helps us reason effectively using a pseudocode that captures the common logical structure of a given task. We demonstrate that Think and Execute outperforms strong baselines like chain of thought and program of thought in solving various challenging algorithmic tasks in Big Bench Hard. Additionally, we show that the pseudocode created by a large language model, LLM, can also benefit smaller LLMs, such as CodeLLMA7B, enhancing their reasoning abilities. To explain how LLMs use Think and Execute, we utilize two components: an instructor LM-I for the think part and a reasoner LM-R for the execute part. The process begins with the instructor LM-I identifying the underlying logic needed to solve a specific task T and generating a prompt that describes this logic in pseudocode. This pseudocode prompt is designed to guide the reasoner LM-R in executing the task efficiently. To kickstart the process, we create a meta prompt to instruct the instructor LM-I in generating a task-level pseudocode for the target task T. This meta prompt includes demonstrations from 3 randomly selected tasks, each consisting of 3 example questions, an analysis, and the prompt P, along with the target task T containing 3 example questions without answers. Section Summary. In this section, we introduce Think and Execute, a framework designed to enhance the reasoning capabilities of large language models, LLMs, by discovering and tailoring a common logical structure for a given task. Our approach involves 3 steps. First, prompting the LLM to identify common reasoning patterns. Second, translating the logic into pseudocode for flexibility. And finally, simulating the execution of the pseudocode to predict the output. Through extensive experiments on algorithmic reasoning tasks, we demonstrate the effectiveness of Think and Execute in outperforming existing baselines like chain of thought and program of thought prompting, showcasing its potential to boost reasoning abilities even in smaller LMs. Section: Step 2. Analyzing the target task. In this section, we analyze the target task by generating key reasoning logic needed to solve it, regardless of the specific questions. For instance, we identify the importance of creating a truthfulness map and updating it through processing statements for tasks like Web of Lies. This approach helps us focus on the common reasoning process shared across all instances, which is essential for creating a task-level prompt. Based on this analysis, we develop a pseudocode prompt that outlines the necessary reasoning steps to solve the task. We choose pseudocode format over natural language plans for its efficiency in describing task logic and guiding the generation of rationales at specific points in the code execution. For example, our pseudocode includes instructions to generate rationales that help track the truthfulness of each person throughout the code execution. Next, we simulate the execution of the pseudocode prompt for a specific instance using the reasoner LM. The reasoner LM tailors the logic in the pseudocode for the given instance and predicts both the final output and intermediate execution steps as rationales. By tracking these intermediate results, the reasoner LM enhances its ability to understand how variables change during code execution. We conduct experiments on 7 algorithmic reasoning tasks to evaluate our approach in zero-shot settings, where no demonstrations are provided in the prompt. We compare our framework with baselines like direct prompting, zero-shot COT, zero-shot POT, and NL planning to demonstrate the effectiveness of our Think and Execute approach in improving algorithmic reasoning. For the reasoner LM, we utilize GPT 3.5 Turbo and Code Llama models, known for their strong performance in reasoning and code generation tasks. The instructor LM is implemented using GPT 3.5 Turbo. Our results show that Think and Execute significantly outperforms direct prompting and zero-shot COT, indicating that explicitly generating a plan is more effective in enhancing ILM's reasoning abilities than solely relying on generating intermediate reasoning steps. Section Summary. In this section, we analyze the target task to identify key reasoning logic needed to solve it, focusing on shared reasoning processes among all instances. We then generate a pseudocode prompt based on this analysis, instructing the reasoner LM to simulate the execution process and predict intermediate reasoning steps to enhance its reasoning abilities. By explicitly generating a plan through our Think and Execute framework, we improve algorithmic reasoning significantly compared to direct prompting and zero-shot cut, showcasing the effectiveness of this approach in enhancing LLM's reasoning capabilities. Section: Task-level pseudocode prompts benefits a wider range of algorithmic reasoning tasks than instance-specific Python code. In this section, we explored how using task-level pseudocode can benefit a wider range of algorithmic reasoning tasks compared to instance-specific Python code. We observed that Think and Execute outperformed other methods in various tasks, suggesting that creating a task-level strategy with pseudocode can enhance reasoning in different algorithmic tasks. We also investigated transferring the logic discovered by a large language model, LLM, to smaller models, Code Llama family. By applying pseudocode prompts generated by the LLM, we found significant performance improvements in CODELLAMA7B and -13B models. Additionally, using pseudocode prompts led to better performance compared to natural language plans. Furthermore, we conducted an ablation study on different components of the pseudocode prompt. We discovered that including comments and semantics in the prompt, as well as printing intermediate steps, significantly improved model performance. Generating analysis before the pseudocode prompt also proved crucial in eliciting a better prompt for solving tasks. Comparing our approach with other baselines, we found that Think and Execute outperformed plan and solve and chain of code methods. Additionally, when compared to self-discover, our method showed better performance, indicating the effectiveness of generating task-level instructions with pseudocode. We addressed several research questions, including the effectiveness of task-level pseudocode compared to instance-specific pseudocode, the impact of pre-training on code corpora on reasoning, and the quality of logic discovered by Think and Execute versus human-written logic. Our analysis showed that implementing underlying logic through pseudocode was more effective than using instance-specific logic, highlighting the importance of task-level instructions in enhancing algorithmic reasoning. Section Summary. In this section, we find that utilizing task-level pseudocode prompts benefits a wider range of algorithmic reasoning tasks compared to instance-specific Python code. Think and Execute outperforms other methods in all tasks, suggesting that applying a task-level strategy with pseudocode can enhance language models' reasoning abilities. Additionally, we observe that pseudocode better describes the logic for solving tasks than natural language, and the components of the pseudocode prompt, such as comments and semantics, play a crucial role in guiding language models to apply discovered logic effectively. Section: Think and Execute requires knowledge in code, RQ2. In this section, we explored whether SLMs can grasp task-level logic written in pseudocode during pre-training on code corpora. We compared the performance of CODELLAMA13B with Llama13B using Think and Execute. Our findings showed that CODELLAMA13B outperformed Llama13B in all tasks, indicating that understanding code logic plays a crucial role in enhancing performance with Think and Execute. We also assessed Think and Execute's ability to generate logic comparable to humans. By comparing Think and Execute with human-written pseudocode prompts, we found that Think and Execute, using GPT 3.5 Turbo as the instructor, achieved higher accuracy, 60.4%, than human-written prompts, 55.7%. This was especially evident in tasks like navigate and tracking shuffled objectives, where Think and Execute showed superior performance. Furthermore, we investigated the impact of LLM's capabilities on Think and Execute by analyzing the influence of both the reasoner and instructor components. Our results revealed that utilizing GPT 3.5 Turbo as reasoners led to higher accuracy scores compared to CODELLAMA13B and Code Llama 34B. The effectiveness of the instructor component, particularly with GPT 3.5 Turbo, also played a significant role in enhancing performance across all configurations. We also discussed chain-of-thought prompting, which encourages LLMs to generate intermediate reasoning steps to guide the solution process. Our approach of using pseudocode in Think and Execute proved to be more effective in zero-shot reasoning tasks compared to natural language plans, as it provided a structured logic for solving tasks. Additionally, we highlighted the incorporation of code in reasoning, where programming languages like Python were utilized to improve LLM-based systems' performance in solving tasks. While other approaches focus on generating instance-specific code, our Think and Execute leverages task-level pseudocode prompts that can be applied universally. In conclusion, although our approach primarily focuses on algorithmic reasoning, we believe that Think and Execute can be extended to other domains requiring complex reasoning sequences, such as multi-hop and symbolic reasoning.